Welcome to Chemistry Exams Prep. This is Dr. Kulbhushan. This question is from Miss Alexis from New York University. In this question, we are supposed to figure out the order of reactivity of the following four reactions. There are these four reactions given, which are free radical halogenation, in this case free radical bromination of hydrocarbons. So in first reaction, the substrate is ethyl benzene, which has a secondary carbon and a primary carbon. It is a benzylic substrate. The second substrate here is allylic substrate. The third one is N-butane, so it's got the primary and secondary carbons. So you can consider it as a secondary substrate because that's the most reactive carbon-hydrogen bond for free radical reactions. The last substrate has a tertiary carbon here, so it can generate a tertiary free radical. These reactions are taking place in presence of sunlight. So H nu is for light and NBS is N-bromosuccinimide. So N-bromosuccinimide actually is used to provide a steady and slow supply of bromine free radical, because in this first reaction, which is called the chain initiation, this NBr bond is homolytically broken and it gives bromine and nitrogen free radicals. So in these cases, basically we need to figure out the stabilities of free radical intermediates that would be generated in each of these four cases. So in case 1, the free radical that would be generated would be a benzylic free radical. This would be the most stable one. The primary would not be stable because the CH bond for bromination, the secondary is better and the tertiary CH bond is the best. So this would be the major radical that would be generated. In case of B, the allyl free radical would be generated, which would be resonance stabilized. The third case is a secondary radical will be generated that would give the major product. There may be some minor product due to primary radical generation, and in case of D, the free radical that would be generated would be a tertiary free radical. So now the stabilities of these radicals is similar to that of carbocations. The free radicals are electron deficient species, just like the carbocations. Therefore, their stabilities would be in similar order, which is a benzylic free radical would be more stable than allylic one, and allylic would be more stable than the tertiary, and tertiary would be more stable than secondary, and least stable would be the primary free radical. So now the factors that affect the stabilities are 4 electronic effects. The first one is the resonance, which is the most important. The second one is the inductive effect, So plus I effect would stabilize the radicals just as the plus I effect stabilizes the carbocations. The third one is the hyperconjugation, which is the stabilizing factor where the sigma electrons of adjacent carbon hydrogen bond stabilizes the electron deficient carbon that bears the free radical. So the interaction in hyperconjugation would be the sigma electrons with the p orbitals. The last one is the hybridization. So if the hybridization of carbon is sp3, that would stabilize the radical the most, and if the carbon that has the radical is sp2 hybridized, it would be less stable, and the least stable radical would be where the radical is on an sp carbon. So now let's draw the products of these reactions. So in case of 1, the product would be the substitution on the number 1 carbon. So 1 bromoethyl benzene would be the product in case of A. In case of B, the product would be allyl bromide. In case of C, the product would be 2-bromobenzene, that is the major product here. In case of D, the major product would be a tertiary alkyl halide, a tertiary alkyl bromide. Bromination of hydrocarbons is very selective. It's more selective than chlorination. So if there is a possibility of forming a tertiary radical, that would be the most reactive. And if there is a possibility of resonance, then that would be even better. So now if you compare the stabilities, in case of first, the stability comes from resonance, inductive effect, and also hyperconjugation. In case of allylic radical, the stability comes from resonance and the inductive effect. In case of C, the stability is due to inductive effect and hyperconjugation. In case of D, again, the stability is due to inductive effect and hyperconjugation. But there are more groups here which are stabilizing the radicals. Therefore, a tertiary radical is more stable than a secondary radicals. So now we can quickly see the choices and see where there is the stability in case of A must be the highest. So in choices A, B and C, the A is not shown to have the highest reactivity in these reactions. Therefore, they cannot be the correct choice here. So the correct answer is choice D here. So now to recap this question and the main lessons, in this question we need to figure out the reactivity of these 4 halogenation reactions of hydrocarbons. These are free radical substitution reactions. Free radical stabilities are the main factors that we need to consider to figure out the reactivities of these 4 substrates. And the stabilities of free radicals are similar to that of the carbocations, because just like carbocations, free radicals are also electron deficient species. There are 4 electronic effects that govern the stabilities. They are resonance effect, inductive effect, hyperconjugation, and hybridization of the carbon that bears the free radical. And the stabilities for hybridization would be sp3 greater than sp2 and sp2 greater than the sp carbon. These out of four factors, the resonance is the most important. So if there is a possibility of resonance, that free radical will be more stable than non-resonance free radicals. So, and due to positive inductive effect and hyperconjugation, more alkyl groups will stabilize the radical more. Therefore, a tertiary radical is better than a secondary radical in stability, and secondary is better than a primary free radical. These were the stabilities of free radicals. Thanks for watching. If you have any questions, please let me know.